Hello students, welcome to Vista's Learning. This is Shruti D. Nadigar, your chemistry tutor. Vista's Learning provides you a very well quality education for all. Yes students, we are going ahead with this. What is this? Can you guess what's the chapter? It's P block elements. As we know, it is the part of periodic table which is placed exactly right end of the periodic table, and we have 6 groups here in which we are learning each group separately with the general properties of P block elements. And this is the chapter 11 and second lecturing class. That means already we have started with this, right? If you have missed any of the videos, students, you can browse into our web application www.v-learning.in. Without wasting the time, we'll get into this. So today we are just going ahead with physical and chemical properties. We have already learnt about the physical properties, right? So we know the 13 group elements. This is what we are learning. In 13 group elements, boron is the first one, and that boron and aluminium we are studying in detail now. So apart from boron and aluminium, all other heavy elements are soft and have low melting point. If you see the gallium will be having very less melting point, such that if you hold it in your palm, it will get melted, and its boiling point is very high, around 2676 Kelvin. So this is the physical properties of 13 group elements. As we know, boron is a non-metal, aluminum is a metal, and going down the group, we get the metallic nature, and they are heavy metals. Did you understand this, students? Good. Next, we have the chemical properties of these 13 group elements. So what about the oxidation state and trends in chemical reactivity? Whenever we need to know about the chemical properties or reactivities, we need to know about their oxidation states. As we know, in 13 group elements, they will be having the +3 as the oxidation state. In the previous class, we studied that, right? So we'll go ahead with these properties which give rise to the chemical properties of 13 group elements. Due to the small size of boron, the sum of its first 3 ionization enthalpies is very high. That means, what is ionization energy? To remove the electron from the outermost orbit, we are providing the energy, right? That energy is very high. Why? Because we have the boron with small size. If you have a smaller size and if you have a larger size, then the nucleus will have, if this is a nucleus, that will have attraction towards the lesser distance, right? The electron which is available in less distance. If the distance increases, then the attraction will be less. So what happens when you have smaller size? The attraction will be more from the nucleus to the outermost electron. So this electron cannot escape or cannot be easily removed. So we need to give more energy. So due to the small size of boron, the ionization enthalpies will be very high. Got it? And this prevents it to form +3 ions. Means generally it will form +1, and it prevents it to form +3 because it have the attraction more. So it cannot easily move. What do you mean by first 3? Means if I have 3 electrons in the outermost shell, to remove 1 electron, that gives you the first ionization enthalpy. If I am removing the second one, that gives you second ionization enthalpy, whereas the third one gives you third ionization enthalpy, means energy required to remove the third one. So likewise, we have first 3 ionization enthalpies for boron, which is very high. And since it is very high, it cannot easily form +3 ions and forces it to form only covalent compound. That means generally boron will not have the ionic form and it will not form easily +3 state as we can do it with aluminium. Instead, it forms a covalent compound. What do you mean by covalent compound? That means boron will share the electron with other. For example, fluorine, if I take, it shares the electron instead of donating the electron. Got it? Good. But as we move from boron to aluminium, what happens? Aluminium can have +3 state. The sum of the first 3 ionization enthalpies of aluminium are considerably decreases as down the group from boron to aluminium, the size increases. As size increases, distance from nucleus to the outermost orbit will increase, and so what happens? Attraction will also decrease. As attraction is decreasing, easily we can remove that outermost electron, and hence aluminium can form +3 state easily than that of boron. So now we have the +3 state of aluminium. We'll just compare with the oxidation state here in the given. Just a while. So here we have the first boron and it comes down as we see here. We have the comparison between the oxidation state of boron, aluminium, gallium, indium and thallium. So down the group what happens? As size is very less for boron, it can form covalent compound. Whereas aluminium can form easily +3 state. But down the group, the +1 state will be more stable as the size is been increasing. And also we know that as we have been spoken here, 10 as we have d orbital, 10 electrons here, 14 electrons, here again 10 electrons and here 14 electrons will be added up. So what happens is that this increases the nuclear charge and the effect of nuclear charge increases, and hence here we get the attraction between the gallium, indium, the attraction will be more. So what happens? The size decreases. As means it is comparatively decreases so that the electrons cannot be removed out. Got it? So what happens? The +1 state will be favorable for the higher elements here or heavier elements, where +3 cannot. Why? One more reason is that in S block, where you go with the gallium, the S block electrons will be 2. They are more attracted than that of p orbitals. If I consider the p orbital, than that of p orbital, the s orbital will be more attracted, and it is considered as an inert pair effect also. We can remove one electron easily rather than that of s orbital. Fine. So we'll go ahead with the chemical properties here. In fact, aluminium is highly electropositive metal, and we have down the group. What happens? The shielding effect increases or decreases. Shielding means the outermost orbit will be shielded by the inner core elements. But here down the group, as we go down the group, what happens? Attraction will be more. So as the attraction is more, the attraction towards the nucleus will be more, and it leads to the poor shielding effect, and that further gives you the poor shielding effect will be given by d and f orbitals, and it increases the effective nuclear charge which can hold on the s orbital electrons very tightly than that of the p orbitals, and so we can remove one electron from the p orbital easily than that of s orbital. As a result, only p orbital electrons may be involved in bonding. So in fact, gallium and thallium, if you see, they will be having both +1 and +3 oxidation states. In that, +1 will be more favorable. So the relative stability of +1 oxidation state progressively increases for heavier elements. As we see here, Indium will have more ability to or stability to have +1 than that of gallium and then that of aluminium. Whereas the +3 oxidation state is highly oxidizing in character. And the compounds in +1 oxidation state, as expected from energy consideration, are more ionic than those of +3 oxidation states. If you see here, we have the trivalent state where the number of electrons around the central metal or a central atom will be having 4 here. Like if you can see, we'll be having BF3. If you see this BF3, boron will have 6 electrons in the outermost shell, right? So what does it do? It have a covalent bonding. Since it have a covalent bonding, F is a fluorine which comes under 17 group. It will be having 7 electrons in the outermost shell. So 2, 4, 6 and 1, right? Similarly, 2, 4, 6 and 1. 2, 4, 6 and 1. So what happens here? Fluorine, each fluorine will share its one electron. Right. So we have BF3 which has been forming. Can you understand here, even after bonding, what is the main motto to bond or undergo sharing of electron or transfer of electron? Main motto is to get the stability. Or if you have the octet structure, that means 8 electrons in the outermost shell, then you will be stable, means the atoms will be stable. If they are stable, then they cannot react. If they are stable, if they have octet rule, if they are following the octet rule or they have the octet structure, then they will not react because they have got the stability. Why other elements are reacting other than noble gas? Noble gas have the octet structure, but other elements doesn't have. They want to meet that octet structure and hence they are bonding and sharing the electrons. Where if you come with the boron, even though it is sharing its all the electrons, all the 3 electrons in the valence shell, it is having only 6 electrons, right? If you see fluorine, each fluorine will be giving 1 electron each, means they are sharing 1 electron each. So 2, 2, 2. 2, 3 is 6. So 6 electrons are beyond the, around the boron. Boron will have only 6 electrons in the outermost shell even after it is bonding, right? So what happens? We get the structure where in this structure it will be p2 hybridized boron orbitals. And this is, what structure is this? Planar trigonal. Okay, we have the planar trigonal structure for this BF3. But it have to get 2 more electrons, right? So what does this do is that this attracts 1 more fluorine atom. That's 1 more fluorine atom. But it is not atom now. It is the ion which already had the electron from other and it is negatively charged. So what happens? This fluorine will come and attract this boron such that we get boron tetrafluoride forming tetrahedral structure. And here the hybridization is sp3. So 3 plus 1, 4. So you will be having the 4 hybrid orbitals. Whereas here you have 2. 2 plus 1 is 3. So hybrid orbitals you can find over here. So hope you understand this, students. So electron deficient, which we have here only 6 electrons around the boron, right? Even after having its bonding. So this we call it as electron deficient molecules. And they can have the capacity to accept the electron from others. So that we call it as tendency to accept the pair of electrons to achieve their stability. Hence, to attain the octet structure, they can attract the electron pair. So as I said, fluorine which is already having 8 electrons, right? This electron pair, it is attracting. Got it? It has a tendency to attract that electron pair such that to attain the stability. And this property of any of the molecules to attract the lone pair of electrons, we call it as Lewis acid. Lewis acid gives you the attraction towards pair of electron. If the pair of electron is being donated, we call it as Lewis base. Got it? Good. Next, tendency to behave like a Lewis acid decreases when the size increases, because the group, what happens? It cannot easily attract. If the size is this and size is this. Okay, I have one electron pair here. So, if the nucleus is here, if the size is less, it can easily attract. If the size is more, even I have the electron pair here, okay, it cannot easily attract this comparative to this. This is very far. So, attraction obviously decreases as the distance increases. So, what happens when you have smaller size? You can attract the lone pair easily. But when the size increases, you cannot easily attract the lone pair. And hence, as the increase in size happens, the Lewis acid character will decrease down the group. Got it? And BCl3 easily accepts lone pair of electrons from ammonia to form BCl3.NH3. Now ammonia, if you are coming with the ammonia, do ammonia have lone pair of electron? That is the main thing. Nitrogen will have 3 electrons in the p orbital and 2 electrons in the s orbital. Totally, it will have 5 electrons as it is an 15th group. In 15th group, how many valence electron we are having? 5 valence electrons, and hence nitrogen is in the 15th group, and nitrogen will have 5 electrons in the outermost shell. 2 are paired, which is in s orbital, and all other 3 will be having the bond pair with hydrogen. So they will have the bond pair with hydrogen, and this 2 electrons are empty here. We call that 2 electrons which are present in the orbital, in the valence orbital, without undergoing any bonding. We call them as a lone pair. These 3 are bond pair, right? This lone pair is now attracted by whom? This BCl3. If you have BCl3, the lone pair will be here in the nitrogen, and that can be easily attracted by this boron. And hence, we get the tetrahedral structure of this complex where boron BCl3 is been attracted towards NH3 to form BCl3.NH3. Hope you understand this. Good. Fine. So, AlCl3 achieves stability by forming dimer. So, we have the dimer. What do you mean by dimer, students? Di means 2, mer means units. So, 2 units of AlCl3 will be attracted towards together and they form the dimer. So, this is how ACl3, this is one structure, this is one structure. So, you can see this ACl3 that will be given by like this Cl, Cl and here one Cl. This is ACl3, aluminium trichloride, and one more aluminium trichloride will be here, which will be like this. So, what happens here is that this aluminium will get attracted towards this chlorine, and this chlorine will be getting attracted towards this, aluminium. So, now they form the dimer like this. So, aluminium trichloride can have the stability by getting or by forming the dimer, because even aluminium will have how many electrons in the outermost shell? If it is AlCl3, it will be having 6 electrons in the outermost shell. It requires 2 more to attain the stability. So how can it attain the stability? By forming the dimer. Got it? Good. So you can also see here the bond length and the bond angle will be given from aluminium to the chlorine. The one which is already bonded through covalent bond will have 206 picometer, whereas the one which is bonded here will be having 221 picometer, and the angle length will be 79 degrees from one chlorine to the other. So next, coming with the in trivalent state, most of the compounds being covalent are hydrolyzed in water. Means they are mixing with water and they are hydrolyzed. For example, if you see the trichlorides on hydrolysis in water, they forms a tetrahedral structure. If you mix the trichlorides into the water, you will get the hydroxide ions which is been attached to this central metal atom. Okay, so it forms this tetrahedral structure of hydroxide. So we call it as tetrahedral species. So hybridization state of elements, element M is sp3 when it is having the tetrahedral structure. Simple students, how to remember this, the structure. Tetrahedral, tetra means 4. So what happens? We have 4 OH ions which is vibrate like connected with the central metal atom, right? Central atom. So if either it is fluorine, chlorine or OH, anything, if they are having 4 here, what happens? There should be the hybridization which is having 4 hybrid orbitals. So we have 3 plus 1 which is giving you 4. So this atom will be undergoing the hybridization with sp3 hybrid orbitals. Whereas aluminium chloride in acidified aqueous solution forms octahedral structure. Octahedral structure will have 6 the ligands we say, or else we can say species. 6 species which is attached to the metal atom. That means aluminium will be here. We'll be having H2O here we are taking. So aqua, hexa aqua, aluminium. So here 1, 2 and here 2, here 2. So we have 6. Octa means it is 8. Don't get confused with that. So you will be having 6 for octahedral. Okay. So we have 6 water molecules surrounding this aluminium which forms octahedral structure. Okay. So we'll be having the structure like this. In this complex ion, the 3d orbitals of aluminium are involved. Obviously, this is the point which we discussed in the previous class, where here we have the d orbital. As we say here 6 ligands are there, here 4 ligands are there. Ligands are those which are donating the lone pair of electrons. So here we have sp3, right? S will have only 1 orbital, P will have only 3 orbital. Maximum from S and P we can have 4 hybrid orbitals. But here we have 6 ligands. How can we get the 6 orbitals? We can get the 6 orbitals by extending to d orbital. We are taking empty or vacant d orbital present in the aluminium, which we can form sp3d2 hybrid orbital. So in this complex hexa aqua aluminium, we have sp3d2 hybrid orbital. Coming back with the reaction with air. We know the metals will react with air easily. What about boron? Boron will not get easily reacted with the air or the atmosphere, and so it will not get coated with any of the oxides. Boron is unreactive in crystalline form. It is not reactive in crystalline form towards the air or oxygen. But aluminium forms a thin coat on the, if I have a piece of aluminium, it will form the thin coat over the surface such that it is reacting towards the oxygen or atmospheric oxygen. So aluminium forms a thin, very thin oxide layer on the surface which protects the metal inside. The metal, whatever which is present inside, will be protected by that layer. So boron will not react with the air, whereas aluminium forms a thin oxide layer. Amorphous boron and aluminium metal on heating in air forms trioxide of aluminium as well as boron. You need to remember, here it is crystalline form, here it is amorphous form. Amorphous means it will be talcum powder like, complete smooth powder of boron. So that will be having a more surface area such that it can easily react with air to form boron trioxide. Whereas aluminium, as we know, it reacts with oxygen or air to form aluminium trioxide respectively. And they also react with dinitrogen. See, generally the nitrogen will not react with any other elements easily. But here you can see that dinitrogen. Dinitrogen is nothing but nitrogen gas, N2. As we are writing N2, it is a diatomic molecule. We call it as dinitrogen. So this dinitrogen, they get reacted at high temperatures. Generally nitrogen will not react, right? It is inert. So it reacts at higher temperature with these elements and forms nitrides. Remember students, it is IDE. So we have nitride, nitrite and nitrate. You should always remember and concentrate on these last three lines, last three letters. IDE means N-3, ITE means NO2 minus, whereas ATE means NO3 minus. Okay, these are the anions of nitrogen. So E represents the element which is reacting with oxygen to form E2O3. Why E2O3? If I take this E is an element, right? What is its oxidation state? We know its oxidation state is +3. Why its oxidation state is +3? Because it is a 13 group element. So 13 group element will generally have +3 oxidation state, and oxygen will generally have -2 as its oxidation state, and when we crisscross over here we get E2O3, and hence we have the product over here. And when this is reacting with nitrogen, we form En. Why it is forming En? As we said, if I take here E is having +3 state, nitrogen is nitride, okay, IDE, nitride will have -3. So as we are taking its standard form, 3 ones are 3 ones are. So we get, when we crisscross one on each, we get En, and hence the product we have E, that is element of the 13 group element reacting with nitrogen at higher temperatures to form En, that is the aluminium nitrides or boron nitrides or any other nitrates of the same group. The nature of these oxides varies down the group. As we know, the properties varies, hence these also matters there. So the oxides also differs there. The nature of oxides varies. As we know, non-metallic oxide and metallic oxide, it depends on the metallic and non-metallic character, right? Non-metallic oxides are generally acidic and neutral in state, whereas the metallic oxides are basic in nature. So as we go down the group, basicity increases because the metallic character increases. So boron trioxide in acidic and is acidic and it reacts with basic oxides to form metal borates. It is acidic in nature, the boron trioxides. Okay, they are acidic in nature as boron is a non-metal. Aluminium, gallium oxides are amphoteric in. What do you mean by amphoteric, students? I have already told you about this amphoteric. That means they can react both with acids and bases. If they are reacting with acid, they become base. If they are reacting with base, they act as acid. So, aluminium and gallium oxides are amphoteric in nature. So, they are neither acidic nor basic. They act both the way. We should not say it is a neutral then. Okay, they are called as amphoteric in nature. And those of indium and thallium are basic as they are heavy and their size increases, the metallic nature increases. As metallic nature increases, their oxides will be basic in nature. So we can see here aluminium chloride, which is been added to the acidified water. We get the complex which is been formed, which have the sp3d2 hybridization. As we just saw before, we have the OH which is been attracted and we get the octahedral structure. And aluminium, as we know, aluminium will form the coating on the surface of the metal, whereas boron will not. The boron will not react with atmospheric air. And when aluminium is added to the mineral acid or base, then it reacts readily and it releases hydrogen gas. Whereas boron will not react with mineral acid or base. So we can see here. We'll just repeat, aluminium chloride which has been added in the acidified water, it forms this complex where aluminium is at the center and all the blue color balls will represent the H2O. So hexa, aqua, aluminium ion will be formed with the octahedral structure. And this aluminium will have the coatings and they can react easily with the mineral acid as HCl and NaOH. And you can see over here, when aluminium is added to the acid HCl, we get aluminium trichloride with hydrogen gas. You can see the bubbles coming out, right? Those bubbles which are liberated are hydrogen gas. You can test the hydrogen gas. How can we test it? We can get a splinter near the mouth of the test tube such that you will get a pop sound, and by that we can confirm that hydrogen gas is released. And we have aluminium trichloride which is been formed by this equation or this reaction. And when this is been added with the concentrated nitric acid, as we know the coating will be there. This is the next example when it is been aluminium is added to the base. When aluminium is added to the base and we get, why we are adding water? Because so here why we are adding the water? The reason is that as we see here, it will not react with HNO3 because it will be forming so aluminium will not react with HNO3 because it will be having a protective oxide layer. As I said, on the top of the or the surface of the layer of this aluminium, it will be formed oxides. So since oxides are formed, it will not react with even concentrated nitric acid also. But when it has been reacted with or added to the base, whenever you take NaOH, NaOH is a solid in state, and when you add water, then you get the aqueous solution of NaOH, that is base of NaOH, and when you add it, we again get the bubbles which is coming out, which is hydrogen gas liberated with a complex which is been formed. We have a complex which is formed here. You can see Na plus Al OH4, right? Tetra aqua aluminate, sodium aluminate, will get it, okay? So this is the complex which is been formed when aluminum is added to the sodium hydroxide and liberation of hydrogen gas. This is the chemical property of aluminum reacting with acid as well as base, but boron will not react with acid or base. Got it? Good. Reactivity towards acids and alkalis, that is what we just saw. Boron does not react with acid and alkalis even at moderate temperature, but aluminum dissolves in mineral acid and aqueous alkalis and thus shows the amphoteric character. Aluminum dissolves in HCl and liberates hydrogen. Hydrogen is H2. So we call it as dihydrogen. So aluminum reacting with HCl to form Al plus 3 Cl minus. This they are in the ionic form. You can just add it up with the AlCl3 as molecule and we get the 3 molecules of hydrogen liberated out. Concentrated nitric acid renders aluminum passively by forming protective oxide layer on the surface. Aluminum also reacts with aqueous alkali and liberates dihydrogen. Reactivity towards acids and again the alkalis. The next point is that concentrated nitric acid renders aluminum passively by forming the protective layer. That is important thing you have to remember. As I said, it reacts with alkali to liberate hydrogen as it gives its property of amphoteric in nature. So we have Al, aluminum reacting with NaOH to form the complex with liberation of hydrogen. Reactivity towards halogen. So as we saw, boron is reacting towards fluorine and forming trichlorides or trihalides. Similarly, aluminum is also reacting with chlorine, bromine and it is forming trihalides of aluminum. So these elements reacts with halogen to form trihalides. Tri means 3. Halides comes from halogen. 17 group elements are called as halogens and we form it as halide. So except thallium triiodide, because thallium is also larger in size. Thallium is also larger in size. Iodine is also larger in size. They cannot easily react and form the halides. So we have this exception of thallium triiodide. E is again a member of 13 group element which is reacting with halogen X2. X is the symbol of halogen. 2 gives you its molecular formula. So X2, it might be chlorine, bromine, iodine, any of them. When it reacts, we get trihalide. As we see here, the E will have +3 and X will have -1 charge. When you crisscross, we get E1X3. So we get EX3 as a product over here. Got it? So we can just go ahead with this. If you see the bromine, when it is been added, bromine is taken in a beaker and we add aluminum, then we get aluminum bromide which is been formed. It is exothermic in nature or high energy is being released and you can see the formation of aluminum bromide. Okay. Hope you are understanding this, students. And bromine is the only one liquid non-metal. You have to remember that. It will be brown in color and it is the only one liquid non-metal. Next, we have this 13 group elements. Why does this boron and the aluminum will have this difference in them? see why this anomalous properties are there, or the difference between boron and aluminium. But the main reason is this d orbital, which is present in aluminium, whereas for boron it is absent. Since boron is in second period, it has only two, that is s and p orbitals, whereas aluminium is in third period, it will be having s, p as d orbitals. So because of d orbital, we have this variation in properties. You can see here aluminium will be forming the octahedral structures or hexa ligands due to the presence of d orbital, whereas boron will not have d orbital and hence it cannot form it. Some trends and anomalous properties of boron. So trichlorides, bromides and iodides of all these elements being covalent in nature are hydrolyzed in water. They can be easily hydrolyzed. Species like tetrahedral and octahedral except in boron. That means we can form the tetrahedral and octahedral species, but boron cannot form it even in aqueous medium. That is the reason why, because we have d orbital for other elements rather than boron. The monomeric trihalides being electron deficient are strong Lewis acids. As I said, boron chlorides, right, or we can take aluminum chlorides or any other chlorides in this group. What happens? They have only 6 electrons in the outermost shell even after bonding all the electrons. So they form the electron deficient. Why? Electron means negatively charged particle, electrons. Deficient means they are less in. So it should have 8 electrons in the outermost shell. Even after bonding, they don't have 8 electrons. They don't attain the octet structure. So how many electrons are less for them? 2 electrons are less. So these 2 electrons are deficient. Less means deficient. So since they have the 2 electron deficient, they can easily attract these 2 electrons from other species. So this attraction of lone pair of electrons or 2 electrons from other will make them strong Lewis acids, such that they can attract the electrons. Boron trifluorides easily react with Lewis base because they are Lewis acids. They react easily with Lewis base such as ammonia. Ammonia is a Lewis base. Why it is called as Lewis base? Because ammonia have lone pair, right? If you have NH3O here, it is having lone pair, it can donate the electron. What is Lewis base? The lone pair electron can be donated, then I can be called as Lewis base. If I am attracting the lone pair of electrons, then I am called as Lewis acid. So here nitrogen have lone pair and it can easily donate the lone pair of electrons to the boron. So boron is Lewis acid and NH3 is Lewis base, and they can get the octet structure such that they can attain the stability. So we have this BF3 which is attracting this lone pair from the nitrogen to form BF3 dot NH3. Generally when this lone pair is been donated, we represent it with this arrow mark from where to where. If it is from nitrogen to boron, we represent the arrow mark towards the boron from nitrogen. It is due to the absence of d orbital that the maximum covalency of boron is 4. It cannot have more than 4 because it don't have d orbitals. It have only s and p orbital. This is the repeated point, students, you have to remember. In second 2s, 2p you have, there is no 2d. There is no 2d. D starts with 3d itself. So we have only 4 suborbitals and we have only 4 covalency for boron. For aluminium, you can extend it. Why? Because aluminium have d orbital and down the group other than boron, all others have d orbitals. So you can have this property of covalency which is having or oxidation of 4 only for boron. Since the d orbitals are available with aluminium, and other elements, the maximum covalency can be expected beyond 4. It can be 6 and more. Most of the other metal halides like aluminum chlorides are dimerized through halogen bridging. As I said you, I showed you, right? Aluminum chloride. So they will be having this bridging. So they form the dimer. One molecule of AlCl3, other molecule of AlCl3, and they combine with bridging with the chloride ions or halogen bridging. We call it halogen. From this molecule to this molecule, we have a bridging like this, right? So this is called as bridging, halogen bridging. So due to that, they form the dimer. Di means 2, mer means units. 2 units combined together by halogen bridging and hence get Al2Cl6. The metal species completes its octet by accepting the electron from halogen in these halogen bridging. So they can easily accept the electron from halogen. So they can get the bridging done and their octet structure will be like met. They can meet the octet structure and become stable. Next, coming with this, we have white fumes appears from the bottle of anhydrous aluminum chloride. Why does this happen? Give reason. You have the answer here. Anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture. We know that moisture is present in the atmosphere. So it liberates hydrochloric acid, which gives you the white fumes. So moist HCl appears white in color. Next one, boron is unable to form BF6 3-. This is general question, student. You have to remember that why boron cannot form BF6. 6 is, it will be forming octahedral structure, right? It cannot form. Why? Because we don't have d orbital, right? So due to non availability of d orbital, you should remember this. D orbital is absent in boron. So that is the main thing. If you remember that, then you can answer any of the question which either they twist any way, you can answer on this boron topic, you can easily answer it. So unavailability of d orbital, boron is unable to find its octet. So therefore what happens? Maximum covalency of boron cannot exceed 4. Got it, students? Good. So we'll just go over here. So here we'll just check with the students. So we have the physical properties of boron, right? So it will be crystalline in structure. You can see its melting point will be 2453 Kelvin. And other, when you go with down the group, the soft metals and they have the low melting point, and we know that gallium will be easily melt on the palm. So these are some of the boiling point of gallium where you can see 2676 Kelvin. We have the physical properties of this, right? So this composition we just missed it, right? We'll just go ahead with this, okay? So here, comparing the oxidation state, as we see here, down the group what happens? +1 state will be more favorable. That will be more stable than that of +3 because of inert pair effect, and SL orbital can be easily attracted by the inner core orbital than that of the p orbital. So what happens? It can easily be attracted as nuclear charge effect will be more. So it can only remove the p orbital, 1 electron in the p orbital, and they can form +1 state down the group. Whereas for boron it will be +3. It is not +3 actually, it will be having sharing of electrons. For aluminum it will be +3, and down that from gallium till thallium will be having +1 state, which will be favorable. Okay, then coming back with this, we'll be having boron, which is having 3 electrons in the outermost shell, and that boron is the gallium. As I said, the size, it will be having the attraction towards the outermost shell easily, and the s orbital, so it cannot easily remove the s electrons. And boron will have 3 electrons in the outermost shell, fluorine will be having 7, and they form the trifluorides. So when they form the trifluoride, they will be having only, you can see over here, you will be having only 6 electrons here. Okay, so you will be having 2, 2 plus 2. So 6 electrons in the outermost shell. So one more fluorine, which is already having the octet structure, it should have 8 electrons. That means it has gained 1 electron and become F minus. That will be attracted towards boron. So boron can attract that fluorine and form the tetrahedral structure. Okay, this is trigonal structure, sp2 hybridization, whereas that is sp3 hybridization of the complex. Okay, this is BF3, that is BF4, which has been formed. Students, by this we finishes, I guess. So we have been done. So hope you understand this, students. By the next class, we'll study the important compounds of boron and their properties, physical as well as chemical properties, and their uses. Hope I understand that the P block elements. Today's class was very helpful for you, and we Vista's Learning always help you with your studies. Whatever you have your doubts, you can get back to us, and we are here struggling to give you the quality education for all. Thanks for watching Vista's Learning.